All right, calculus students, let's get into calculus stuff. Intro to derivatives. Okay, this is where the class really starts. We use the concept of a limit to understand what a derivative is and how it's calculated. But before we even worry about limits, we talked about how slopes, like slope values, equal rates of change. A pitch of a function can tell you how quickly the function is moving. I'll go straight to like a graphical representation. Here is a function. We're worrying about the average rate of change of the function from 2 to 4. Well, I got this 0.22 and I got this 0.4. Oh, we'll call it -2. Well, if we connect these 2 points with a line and calculate the slope, we can see like how many y's we decreased over how many x's. Now, you could do this by rise over run. You could use it using the slope formula, but like you went down 4 y's, like I went down 4 y's over the course of going over 2x's. Okay. Now, you could say, oh, I went down 4 y's per 2x's, but when you divide these two, you get a rate of change. You get, down 2 y's per x. You can write a statement making sure you understand what this value means. You can say, on average, over the interval from 2 to 4, my function decreased or went down. I'll just use went down 2 y's per x. Okay, slopes, rates of change. From -1 to 4. Now, like obviously the function's like decreasing like slower than quicker than slower. So like this is why it's an average rate of change. It's not telling you exactly how the function's changing. It's just saying like, yo, on average, if you go from here to here, that's how much you changed. This function goes up and then down. If you're talking about overall from -1 to 4, since you have no change in y, you'd say on average, I didn't go up at all. So like I went up 0, I went down 0 over the course of 1, 2, 3, 4, 5. And again, you do y2 minus y1, x2 minus x1. But that's 0 per 1 or 0 per whatever, or 0 y's per x. So slopes of what we call secants tell us an average rate of change of a function. I'm going to say the function did not go up or down over the interval, or was like constant. Yeah. It's not true though. Like on average, the function was constant, but we can see the function went up and then down. It went up a bunch, it went down a bunch. On average, though, we end up where we start. Now, we go into the next concept of an instantaneous rate of change, like how quickly the function is changing at a point. And this is where we would understand and visualize the concept of a tangent slope. Now, calculating the value of this tangent slope, that's what was like the brilliant discovery by Newton in the 1600s. The slope of this tangent line gives you the instantaneous rate of change of this function at x equals d. So that slope, which is negative, is telling you how quickly the function is decreasing at that point and at that point's location. Okay. This is where we then like create the graph of its slopes, we have this new equation, and this is where like math changes. Typically, when I ask you to like analyze a function, like, hey, look at this function, tell me what's going on with it, you would then look at the function, or you would analyze and like do different techniques with the equation of this function. What we are going to do in this class is like say, okay, cool, you want me to analyze this function? Let me find the formula for its slopes, the formula for its derivative. Let me find the formula for the instantaneous rates of change of this function. And you're actually going to use this other equation. This other equation will then provide you information about this equation. Okay, so that's the basis of this lesson. Slopes are change, and the basis of the entire first semester. Slopes are change. Slopes of tangents, instant changes, that's derivative. Slopes of tangent will come from a different equation, a different formula. We'll use this different equation to help us understand the slopes of the original equation. And we'll get there. Let's just go back to the beginning where they say find the average rate of change. And again, you're thinking slope over an interval or slope of a secant. And you honestly can use the slope formula for this. Change in the y's over change in x's. Slope formulas are what we use. The slope formula is what we use for an instantaneous rate of change equation. So all you need to do is spend time just plugging in the points on your interval. They always give you the interval. And then just calculating the slope. 8 to 27 is up 19. You can find that by subtracting. You subtract it to find like distance in between. And I said I went up 19 over 1. You say on average from 2 to 3. My function goes up 19 y's per x. Okay. Next one, 0 to 3. Let's find the y coordinates, find the slope of the secant. 9 times 2 is 18. 18 minus 9 is 9. 9 plus 2 is 11. If I make any mistakes throughout this homework video, I apologize. I went up 9 over the course of going over 3. So 9 over 3 or 3 is the answer. If you want to use the slope formula, go ahead. Change in the y's is how much we increased with our y's. Change in the x's is how much we increased for our x's. So I went up 9 y's over the course of 3 x's, 3 y's per x. On average, my function went up 3 y's per x over the interval from 0 to 3. Okay, and now we can compare these two numbers. It's like, oh, this one up 19 y's per x, this one up 3 y's per x, this one increased faster on average. Plug in 0. Let's plug in pi over 3 first. Get the cosine of 2 pi over 3. Negative a half. Cosine of 0 is 1. So I went down 1.5. If you want to use the slope formula, I went down 3 halves over the course of going over pi over 3. From 0 to pi over 3, I add pi over 3. So this is telling you like what happened over the interval. When you divide the two numbers, you get a rate. Went down 9 over 2 pi y's per 1x. So on average, this function went down 9 over 2 pi y's per x on the interval from 0 to pi over 3. Some others, just got to plug through these. 2 to the -4th. Good little review of exponents. Negative exponents is a reciprocal of a positive exponent. 2, 4, 8, 16. It's not 8, it's 16. So I went down from a half to a 16th. I'll have to find a common denominator to find that. Over the course of 3x's. This is 8 sixteenths, so I went down 7 sixteenths over the course of 3x's. Dividing by 3 is the same as multiplying by a third. Went down 7 sixteenths over the course of 1/3. 7 sixteenths times 1/3. What's that? 48. I went down 7 y's per 48 x's, or I went down 7/48ths of a y per 1x. On the interval from 1 to 4. So I know the answer of this is -3 right off the bat. Because lines, guys, are consistent in how they decrease. 4 minus 3x, it's decreasing the slope of the line. The slope of the line will be the slope of the secant. You can go ahead and just say, boom, -3. I understand what's going on. I understand the concept of slope. I understand if we're talking about a line, the rates of change are always going to be consistent. But let's just go ahead and confirm that the answer is going to be -3. 4 minus 15 is -11. 4 minus 3 is 1. So from 1 to -11, I went down 12. If you want to subtract to get that. I don't like to use the slope formula often, like when I can just see from here to here, what did I do? I went down 12. From here to here, what did I do? I went up 4, over 4, because we're talking about x's. And just like we suspected, the answer is -3. I can say on average, I can say the function consistently decreases at 3 y's per x. But whatever. Tangent of 3 pi over 4 is -1. Tangent of pi over 4 is 1. So I went down 2 from 1 to -1. Down 2. Over the course of, I can think about pi over 4 to 3 pi over 4 being 90 degrees. So it's pi over 2 if you want to do the math. 3 pi over 4 minus pi over 4 is 2 pi over 4. 2 pi over 4 is the same as pi over 2. Keep the top, -2 over 1, multiplied by the bottom flipped, giving us -4 y's per pi x's, or I'm going down 4 over pi y's per 1x, a rate of change. The interval. Okay. So average rate of change, we talked about it. It's the slope of a secant. Slopes, rates of change. We already found the average rate of change. We can find, any two, like from here to here, from here to here. It just talks about on an average. Doesn't help you find what's going on at that location. Okay. And this is where we say, well, let's examine what's going on right at 1. Okay, right at 1. What's going on right there? And we talked about how, well, if slopes tell you how quickly things are changing, the slope at that point, pretend that line is like just touching right at that location. Slope right at that point will tell you how the function is changing at that location. But how can we find that slope? Using the slope formula, using nothing like fancy, just like the slope formula. Well, we can start by like approximating it. It's like, well, let's go like to the left and to the right and see what we do. Like, why don't we just use the points -2 to 4? Well, this would not be good because I can see like I'm looking for a positive slope. And if I did from -2 to 4, I go down 2 over the course of going over 6. So I go down 1/3 of a y per x on average. Not going to be a good approximation of this. But let's go from -1 to 3. Well, -1 to 3, at least the slope here, at least it's positive. At least it's better. It's closer to what it's going to be, this slope, which is some positive slope. But it's not going to be right because this is going to be shallower than the line that I see here. And again, like this is the line we're trying to focus on, and its slope value is what we're trying to approximate. So from -1 to 3, I am going up 2 over the course of 4. So 1/2, better. 0 to 2. 0. I'll come back. Froze. We'll use the green pen. There we go. 0 to 2. This is going to be even better. If I looked at this line that connects those 2 points, that line is going to be closer in terms of its pitch to the line that we're trying to get here right at 1. So it's like the closer and closer we get to the point, the better and better the approximation is going to be using the slope formula. Here I go up 1.5, 2.5, 3.5. I go up 3.5. 3.5 is 7/2 over the course of 2. I go up 7/4 of a y per x. Like this is better. This is better. Better. If I had the information, okay, if I had the equation, let's say I had the equation of this function, some cubic maybe function, but if I had that equation, and if I had a calculator, what would be 2 better points to use? Well, like 1/2 and 2 and 1.5 would be better. If I used this point here at 1/2 and this point here at 1.5, like the line that connects those 2 points would be better. It'd be almost very close to the exact steepness slope value of that line right at 1. And then we talked about like, guys, what have we been doing all last unit? We talked about like going infinitely close to locations using like the 0.9s or the 0.001s. If I had information where like I could plug in 0.99999, find the y value, and I could plug in, let's just figure out the points. And if I could plug in to an equation 1.0001 and find that y coordinate, I could subtract those 2 y coordinates and then subtract those 2 x coordinates. I'll be dividing by something that's close to 0 because 1.001 minus 0.999 would be very close to 0, but it's not 0. You can't use the slope formula at 1 because if you use the slope formula at 1, you'd get 0 over 0. I don't know what 0 over 0 is. But if you don't divide by zero, if you divide by something close to zero, you can do that. So this is the idea behind like why we use limits in calculus. Because like using a slope formula, but the points are infinitely close together rather than on top of each other, we can do that. That's something we can do. Okay, so this is the idea we can think about, but we're not going to use this idea. Besides, it'll help us create a formula. So at least it's an introduction to like why were limits important. Okay, because we will use limits to help find our slopes of tangents. And slopes of tangents are instantaneous rates of change. We have to be comfortable with the following. If I ask you for the instantaneous rate of change of a function at a location, I'm asking you to find the slope of the tangent. And a fancy word for that and that is derivative. It's quicker to say, and that's what a derivative is. It's just a slope of a tangent. Okay? Okay, so like we did this in class. We are looking at x cubed, and we're trying to find the instantaneous rate of change at 3. We have a slope formula, and we have a calculator. You won't have a calculator in this class. This procedure that we're about to use, we don't use because it's just not a realistic process to use if you don't have a calculator. It's actually what your calculator does do if you ask it to find a derivative. I'm not going to like show you how, like what you type in when you ask the calculator to find a derivative. Like there's a button that says like, hey, find the derivative. But all your calculator does is actually use points that are very, very close, and it uses a slope formula. So let's just like go for it. I can do this by hand. Let's find the average rate of change from 2 to 4. Well, 4 cubed, I'll use the calculator. 4 cubed is 64. 2 cubed is 8. So I think the slope's going to be close to 28. Okay? 2 to 4, if you look at x cubed, okay, 2 to 4 will do a decent job of approximating what's going on right at 3. That's slope. But 2.5 to 3.5 would do it even better. I'm just going to go ahead and plug things into the slope formula. I'm going to get the answer right away. And you're not going to be asked to do this on your quiz. This is more just demonstration purposes. Okay, the slope of the secant between those 2 points is 27.25. All right. It's going to be a better approximation to what's actually going on right at 3. Let's plug in 3.1 and 2.9. This would give us a better approximation because the 2 points are closer to the location of x equals 3. .01. I can see I'm approaching a very specific, a whole number. I'm approaching 27 probably, but let's just double check. If I plugged in 3.01 and 2.99, heads up, calculator trick. You can insert, press second, insert a value, insert, don't need to insert there, 27.00. Okay, so could we continue this process? Yes. Could we do it without a calculator? No. What do we think the instantaneous rate of change or the slope of the tangent or the derivative of y equals x cubed at x equals 3 is? Using my calculator, I'm assuming it's going to be 27. Okay? But Newton didn't have calculators. Okay? Newton understood the idea behind this. Newton needed another way. Okay? And Newton discovered this beautiful idea, this beautiful discovery of a tangent slope function, a derivative function, and a derivative equation. Newton understood that if you looked at the tangent slopes to a function, again, let's assume this is x cubed, the one we just looked at. Okay, and if you plotted the tangent slope values, understanding that lines that are pitching up, the slope is positive. Lines that are pitching down from left to right, the slope is negative. Lines that are flat, the slope is 0. And we could also understand that like this slope would be more positive, it'd be a bigger value than something that's shallower, right? A very steep line that goes down would be a larger negative value compared to a shallow line going down. That would be less negative. I'm just gonna like approximate tangent slopes, understanding that like positives go above the x-axis, negatives go below. This slope is very positive. This slope is less positive. This slope is 0. This slope is a little positive. This slope is more positive. And I'm just gonna like, take some x values, like here, this is -2, this is -1, 0, this is 1, this is 2. Or I could say like this is -3, -2, -1, 1, 2, 3, because we're trying to find the slope at 3. And we could say, okay, very positive, less positive, 0, positive, very positive. And if we looked in between, we'd see that our slope values, if we connected all of our slope values, that they form this U shape, this graph that has an equation. Okay? Now, here's the big discovery. If you could find the equation for this graph, okay, and we will find them quickly. For right now, I'm just going to give you the equations. Like, you won't have to find them. I'm going to be like, I used this process Newton discovered. I found that the f prime equation for f is this. And then I'm going to be like, what is the slope here at x equals 3? Well, we will find that this y value right here at 3, we'll find that that y value is 27. The y values on f prime tell you the slopes of f. And this is like how we're changing our whole thoughts with math. To analyze a function, we're not going to look at the function. We're going to look at its derivative function, its tangent slope equation. Okay? So, very important. The y's of f prime give you the slopes of f. You need to hold on to that understanding. You got to understand that if you have an f prime equation, its values, its y values, give you the slopes of f. Okay? We'll find out what this equation is in a second. We actually did it in class. But for right now, like you gotta be able to see how every function is going to have its own unique derivative function, its own unique tangent slope value function. Not all of our f primes are going to look like u's. For example, take this function, looks like some negative x squared. Maybe a negative x squared plus a 4 or something like that. If you Look at the tangent slopes, and again, use as many points as you want. You realize the slopes are positive, less positive, to a 0, to a negative, to a more negative. If you plot those slopes, positives, less positives, zeros, and again, I'm going from left to right because I'm like taking X values. And it's like, oh, at -4, the slope is super positive. At -4, the slope is super positive. This is like how I'm doing this. I'm not just plotting these points randomly. So this is very important when you're doing this process. Like, understand the locations matter. Negative, more negative. We realize that this line, there's some sort of line equation. And this line equation, whatever it may be, its y values will tell us the slope values, the exact slope values. The exact slope values are how quickly the function is changing at a point. Okay, it's different than using a limit. It feels like it's like, where did limits go, Mr. Mester? Where did the 3.001 go? Where did the 2.999 go? Don't worry, it'll come back. Okay, this seems different, but don't worry, it'll come back. Close to 0, positive, more positive, more positive, more positive slopes. Coming from like -2. Close to 0. Let's just assume that it's not 0, but it's close to 0. Close to 0, positive, more positive, more positive, looks to be something maybe like this. And again, if we could find this equation, we could find y values on this graph, and the y values on this graph will correspond to the slope values on this graph. Beautiful, beautiful, like discovery. Again, doesn't seem like it has 0.9s involved, but it'll come back. Super positive, less positive, less positive, less positive. Super positive, nothing over here on the left side. I have no like graph on the left side, so I'm not going to put any slope values over here. Super positive, less positive, less positive, less positive, less positive. Cool. So whatever graph this is, actually looks like a log graph, like y equals log x. This equation that generates this graph, the y values on this graph, whatever this y value is, that tells me, let's say this is right here. Let's say this is 1. The slope right there is 1 because that's the y value there. Okay. This is a fun one. Let's look at some specific points. I'm going to go and focus on like the zeros on this graph just to kind of mess you up. It's not the fact that it's a 0. The slope is negative. This slope is 0. This slope is positive. Slope close to here is 0. This slope is negative. This slope is 0. This slope is positive. Okay? This is some sort of like x to the 4th. Well, if I do like 1, 2, 3, at -3, my slope was negative. At -2, my slope was 0. At 1, my slope was positive. Close to 0, my slope was 0. At 1, my slope was negative. At 0, my slope is 0. At 1, my slope is negative. At 2, my slope is 0. At 3, my slope is positive. Now, you have to figure this out by yourself. We get something that probably looks like this. Okay? So it's some sort of cubic. Now, the whole purpose of this is to see that like there is some equation, okay? This equation, which we'll be able to find soon, but for right now, I'm going to kind of just tell you what it is. This equation is unique. It's very unique to its original function, okay? It's like its buddy. It's its tangent slope buddy. And again, this equation will give you these y values. The y values on this, so let's say, I don't know, this value is 5. There's that point with a y value of 5. That means here, that slope is exactly 5, okay? That's important. The y values on f prime tell you the slopes of it. Seems like it's no limits, no 999s, 0.001s. But we'll see how the equations are actually generated using like the idea of a limits, okay? And that's because in class, we developed what is a formula for finding these equations. We started with some sort of function, say it's like this cubed. And we said, well, let's just call this point some point at x, this point some x plus some distance. So I like distance away. And let's just like write down the slope between these 2 points, like theoretically, where this is some random f of x function. And so this would be the f of x point, and this would be like an f of x plus h point. Well, y2, this y coordinate, minus this y coordinate, so minus y1, over x2 minus x1, x2 minus x1. This gives me a theoretical slope of 2 points h distance away from each other on the x-axis. Now, we can see like it's just about the h distance. Like this h distance is the change in x's. It's like how much we went over. So like the x's really go away. And you get this formula for slope. Hey, if you know how far away your points are in terms of an x distance, y2 minus y1 divided by that x distance. That's a slope formula. No big deal. It came from slope. Well, if this distance between those 2 points are infinitely small, if you're using 2.9999 and 3.00001, the distance between those points is close to 0. If we take this distance and make it close to 0, my friends, this is the idea that combines like slopes and limits that gives you your better and better and better and better and better approximation, your best approximations. If you keep getting better and better approximations, you're going to approach the actual. This, my friends, is how we're going to find the equation of f prime that we just graphed. We're going to use this formula. I'm going to use the formula. You just need to know where the formula comes from. This formula will generate rules so that we don't have to use it. We can just say, oh, if our function looks like this is its derivative. The rules come from the formula. So this is just slope of 2 points practically on top of each other. This is the same thing, only instead of h distance away, we're talking about a point at x and a point at c. As x gets closer to c, this point will get closer to that point. Boom, that'll be a tangent slope. Slope of 2 points infinitely close to c. Okay? To kind of practice your understanding of this, like I'm going to say like, hey, here's a graph of some function, f of x. What's that? And you're immediately like, I have no idea. Well, again, slope. Infinitely close to each other, 2 points. H distance is close to 0. So the x distance is practically 0. Focusing on the point f of d. Okay, here's d. There's f of d. So we're talking about the slope of 2 points close to each other right around d. Oh, this slope is negative. My value is negative. I'm looking at this line that's negative. This is the same as that. It just looks different. It's like y2 minus y1, x2 minus x1. X is getting closer to d. So as x gets closer to d, this gets closer to 0. As I get 2 points close to d, boom, I have this slope. Again, it's that slope. Now notice this does not have a limit next to it. This is just f of d minus f of c. This is just your secant slope formula. For this one, we focus on the slope between these 2 points, c and d. I'm going to just say, like, that's less negative than that slope. Yes. You have to go down that hallway, down the stairs. This secant slope again, but now it's between A and C. Now, the slope of this line, I know is super positive. It's going to be a big value. This, okay, y2 minus y1, we're close to 0 on the x, so we're talking about 2 points infinitely close together. Okay, well, this goes back to being like tangent slope. This is the combination of your knowledge of limits and a slope formula. We understood limits from last unit, but now we're applying limits to a slope formula. This becomes tangent slope. Well, this is giving me my tangent slope at C. The tangent slope at C looks to be close to 0. This, okay, x is approaching b, so we're getting close to b. Don't plug in b because then you get b minus b and you get 0 and you're like, oh, I can't do 0 over 0. And you can't simplify this. But plugging in something close to b, all right, we're talking about a point at b and a point infinitely close to b. Infinitely close to b. Connecting and extending those 2 points, boom, we get that tangent equation. That tangent slope is positive. This, again, is a slope formula. This is just the slope of the tangent. This is the instantaneous rate of change. This is the derivative at b, which is like probably more positive than any other value. It's probably more positive than the secant slope. Like, I was going to say more positive. So what you're going to be asked to do potentially is like order things from least to greatest. So if I asked you like, hey, what's less than what, then less than what? You'd say, yo, this is the most negative. Okay, so this is the least value. This is less negative. That'd be the second least value. This would be tied for first because it's the same thing. This is 0. So this is, the third least value, like super negative, less negative, 0. And then we go to positives. Then we go to more positives. Okay? You can order things just by, analyzing, the steepness of the slopes, and you're good. Okay? Now, we've combined our knowledge of limits with a slope formula to develop this magic formula. Okay? And I did this once in class. You will not have to do this ever. Okay? But what I did in class was I took this and I plugged it in here. It's a bunch of like algebraic manipulations. It changes some stuff. I'm going to change this to just be x cubed. I'm not even going to do x cubed minus 1, just x cubed, so we can go back to our first problem. And it's the same thing. Nothing changes. When I plug this in here, I found that f prime is 3x squared. F prime is 3x squared. If I plug in 3 and get this y value, I get 3 times 3 squared. I get 27. That number's familiar to us because I did this. You just have to know like what you have if I give it to you. I plug this into the slope slash limit formula. And what I found is that this equation, if this is x cubed, the equation for its tangent slopes are 3x squared. Where did I come from? Where did I get it? I plugged in x cubed into this magical limit slash slope formula. Boom. It magically created the equation for tangent slopes. This helps us find these y values. Plug in 3, you get 27. Boom, that slope's 27. In class, we plugged in 2. We got 12. This y coordinate at 2 is 12. That's telling me that this slope at 2 is exactly 12. Plug in -1. Plug in -1 squared, you get 1 times 3, you get 3. This y coordinate at -1 is 3. That means this slope at -1 is exactly 3. This was like the discovery, okay? You don't have to use a calculator. You can understand limits, understand slope formula, combine the two, create this magical formula that gives you a new equation that will give you slopes. Its y values will give you slopes of the original equation. We're going to be asked like, hey, tangent slopes of x cubed at x equals -1.5. You're not going to do anything with x cubed. This graph, it's like, okay, great. I want to know the tangent slope at -1.5. You don't use x cubed. You actually use its friend, its buddy, its tangent slope generating formula. You will use the formula for this graph, okay? So this is what's really different about this class is like, you're going to be asked to find stuff about a function. You're actually not going to use the function. You're going to use its derivative function. This is Mr. Messer. Thank you. Can you tell them to give me 5 minutes and I'll be over there to pick them up? Appreciate it. Thanks. Okay. This meaning is this is the tangent slope, which is the instantaneous rate of change, which is the derivative of f of x, which equals x cubed at x equals 3. It's gotten from a different equation. That different equation, its y values tells me the tangent slopes to the original equation. What is f of 3? All right, well, if I plug in 3 into this, I get 3. Now I get 27. Now, I don't like how we get the same values, but whatever. But we talk about how if you combine a point and a slope, you have an equation of a line. Using this point slope formula that we used a lot in Algebra 1 and geometry. Now, what's important about this is like, this is a tangent slope. The tangent slope comes from f prime. This is the point on f. point on your original function. Okay, so 3 goes there. This 27 goes there. This 27, I'm going to change up the point too. That 27 goes here. Y minus 27 equals 27, x minus 3. Let's change it up so I get different values. Let's look at x equals 1. Okay, so again, we're analyzing x cubed, whose tangent slope equation graph is given to you by 3x squared. I found it for you. You right now just need you need to know how to use it. If I plug in 1, let's go. I don't like getting the same numbers, so I want to change it. Whatever, it's fine. The next one will be good. I plug in 1, I get 1. This is a point on my function. I plug in 1, I get 3. This is the slope of x cubed at x equals 1. Y minus the point on my function, x minus the point on my function, the tangent slope comes from the equation of our tangent slope. The y coordinates on f prime gives you slopes of f. 2 more points, we got it here. Plugging in 2, I get 8. Plugging in 2, just going to write down the equation again. Plugging in 2 here, and this is what we did in class, gives us 12. Point, tangent slope of f at x equals 2. Y minus 8 equals 12, x minus 2. Plug in -2, I get -8. Understanding this is the equation that gives us the tangent slopes. Plugging in -2 gives us positive 12. Slope of the tangent, point on the function. Okay. Now, I'm asking you to do the same thing as we did before, but with these different functions, okay? I'm just going to do one of them, okay? I'm going to do this one at x equals 2. And I'll do this one. I'm just going to pick a different x value, x equals 1, okay? Now, again, we have different equations. This is a different equation. This is no longer just x cubed, okay? This is some sort of quadratic, a u. Its tangent slopes, and again, where did this come from? I did it for you, okay? I plug this into our magical formula that combines limits and slopes. Boom, I got that equation. It's essentially, we start with this u, and we find this equation of this line. Okay, and I can just do it right down here. I'm focusing on 2. So let's plug in 2 into this function. I get 4 plus 6, which is 10, plus 2, which is 12. I don't like how we always get 12, but whatever. If I plug in 2 into this, into f prime, I get 7. That's telling me that this y coordinate at 2 is 7. That means this is the tangent slope to this function at x equals 2. So I get my line, y minus y1, this is the point, this is the slope of the tangent at that point, equals 7, x minus 2. It's that simple. Take any x coordinate, plug it into this, -1, -2, -3, -4, a half, a quarter. Plug any of those points, any of those x coordinates into this, and the y value you get, like plugging in -1, I get 1. The slope of this at -1 is 1. Plug in -2. I get -4 plus 3, that's -1. So at x equals -2, at -2, the slope is -1. 4 plus, so that's it. That's the tangent slope, but I'm giving you the line. 4 plus -6 is -2, plus 2 is 0. We now have an equation, y minus 0 equals -1, x minus -2, which is the same as plus positive 2. New equation, different equation. A different x cubed, an x cubed plus an x squared. I took that equation, I plugged it in to this magical formula that combines our knowledge of limits with our knowledge of a slope formula. I plugged it in there. I'm not going to show you all the work. It takes too long, and it's just going to be confusing. It's just like you're going to be able to do this very quickly because this formula here generates rules. So we can easily get f prime equations when we look at f equations. Okay, so but for now, I'm just going to trust me. I plugged in f into this, and after I plug that in, I got this f prime. The y coordinates here tells me the tangent slopes here. I'm going to decide to focus my attention on 1. I'm just picking a random x now value. If you plug in 1 into f, it gives you a point on f. 1 plus 1 minus 2 is 0. If you plug in 1 into f prime, it gives you the slope of the tangent at this point. Beautiful. It's like, man, you want to find slopes of tangents? You don't need a calculator. You don't need 0.9s. Like, you just find an equation, a formula. This formula, this f prime formula, we're using it. It's so powerful that there's an equation that gives you how a function is changing. So powerful that we're going to focus all attention on, like, what else can f prime tell us about f? What else can we do with these f primes? It's awesome. And you get this equation. Y minus 0 equals 5x minus 1. What's great is you can graph this. Now, you won't be able to do this, but this is like something that's fun to do, fun for me, when you have the capabilities and you can do it quickly to check your work. Here's this x cubed graph. I don't have to solve for y much because it's y minus 0. If I wanted to, it's very easy to just like add this y value over. I'll do this for both of them that I found. And you can see your x cubed graph, the x cubed plus the x squared, and you can see your tangent slope equation that you just generated. The slope of this line is 5. That's the slope of the tangent at 1. Let's do this for the x squared graph at -1. X squared plus 3x plus 2. Don't graph f prime. F prime just gives you values that you use. I'm not graphing f prime. I'm graphing the line. And again, it's a y minus 0, but it's very easy. Like you don't even have to distribute anything. I don't ask you to solve for y and put it in y equals mx plus b form. It's not necessary. We had the point -2, 0. So like slope x minus x1, and then like you could just add this number over if it was anything other than 0, just to show you like it's easy to just have an equation solved for y, even though it's not mx plus b form, and that's fine. But what's great is like this is going to be over here at -1. Sorry, -2. So at -2, there's that equation of that tangent line. Okay? I hope you understood this. Like this is the beginning of the rest of the semester. The existence of an f prime equation whose y values tell you the tangent slopes of f. Calculus starts now. Good luck out there.